We just were looking at these balanced nuclear equations from a standpoint of calculating the mass defect. But we also need to take a little bit of time to talk about what the point is when we're doing balancing nuclear reactions. So that means we should probably even take one step back and remind everyone of what we mean by balancing reactions. So when we're looking at balancing reactions, what we're looking at is all the mass, or maybe we could even say all the stuff, on the reactants side of our reaction has to be equal to all the stuff on our product side. Now, when we just were balancing chemical reactions, then we were following our little rule that no matter can be created or destroyed. And we still have to be consistent with this, only we also need to remember that now we do have energy and mass conversion. So when we do energy and mass conversion, we aren't creating or destroying anything, we are converting it from one form into another. So when we look at balancing nuclear reactions here, in chemical reactions, all of our elements stayed the same. So we had the same number of each kind of atom on each side of the reaction. So this is like if you were cooking, all of the ingredients that you started with ended up in whatever the thing was that you cooked. And you didn't have some of it disappear. If you didn't use all of the onion, some of the onion went back in the refrigerator. It's all accounted for. So when we're doing nuclear reactions now, we have to pay attention to something a little bit different because not all of our atoms are staying the same. As you can see in these reactions up here, we're converting some of our elements into different elements. Sometimes we're breaking an element apart. Sometimes we're adding some mass to it and turning it into something else. So instead of paying attention to the number of each kinds of atom on each side, now we're going to pay attention to the total mass and the total charge. So this leads us back to our isotope notation. Remember, a really long time ago, we did isotope notation, and we said that for each element, we're going to list for our complete isotope notation over here the mass number, which we give a capital A, and down here on the bottom left, we have the atomic number. So that was before when we were only looking at individual elements that don't change around. So now we're going to stick with these mass number and atomic number, but we're going to expand our definition to include some things that don't have protons, right? Because the atomic number was the number of protons before, and the mass number was the protons plus the neutrons. So now we're going to pay attention to the mass number still, which is going to be the protons and neutrons. But this is going to actually be the charge overall, because this allows us now to include things that don't have charge, like neutrons. So a neutron is now going to have a mass of 1, but no charge. We'll have protons that have a mass of 1 and a charge of 1. We have electrons that have no protons or neutrons, but a charge of a -1. We might also call this a beta particle, which is the same thing. And we can also have a positron, which is the opposite of an electron, an anti-electron. And so that's going to also have no mass, but a charge of a +1. And of course, we've already seen the alpha particle that has 2 protons and 2 neutrons, which means that it has a mass number of 4 and an atomic number of 2. So these are all of our kind of subatomic plus our helium nucleus that are involved as mini particles that we're going to see both coming into nuclear reactions and coming out of nuclear reactions. So the key to balancing is that the mass numbers must balance, and the charge numbers, what used to be our atomic number, is now our charge number. They must balance on both sides of our reaction. So if we look at an example reaction, one of the naturally occurring radioactive elements is carbon-14, which we use for carbon dating. And carbon-14 is a trace component of carbon that is present, in all kinds of things. And we slowly absorb a little bit of it, and when it decays by beta emission. That means that it gives off an electron. So let's put in the electron. It has 0 mass, but it has a -1 charge. So when we are going to balance this equation, the way that I do it is I first look at my mass numbers, and then I look at my charge numbers, and then I figure out which elements or which element I need to put in my little, empty space here to make things balance. So if I look at my reactant side, my mass is a 14. So over here I have a 0, and I need to have this add up to 14. Since this is a 0, that means this element is going to also have a mass number of 14. Oops, let's fix that. Now I look at my charge number, and on the left-hand side it's a 6. And on the right-hand side I have a -1 plus something, and that has to equal 6. So that means this number has to be a 7. So if I look back at the periodic table, I can see that the element with a mass number of 7 is going to be nitrogen. So you can identify which element you need to put in your balanced equation, in your balanced nuclear equation, by just making sure that your mass numbers and your charge numbers balance out. We have a couple of different ways that radioactive elements can decay. So we just saw beta emission. And beta emission gives off an electron. You can also have alpha emission. And in that case, the radioactive isotope gives off an alpha particle. I guess we better put in our little isotope notation so we can balance it. Those are the two most common kinds. You will sometimes have electron capture, and that means that we have an electron going in. And then the other thing, these are sort of, natural decay processes, but the other thing that we also see is fission. And fission usually happens because we add one or more nitrogen, and the main atom splits. And the atom will split into one or more parts. So we saw we saw some examples of fission up above here. So these 3 examples that we looked at with, there we are, our first one, with the uranium-235, we added a nitrogen, and then the uranium split. And we had 3 different ways that the uranium split. So these are 3 different ways that the U-235 can undergo fission. So when you go through these examples, you can see that our mass numbers are all going to balance and our charge numbers are all going to balance. And it would be a good idea for you to double check those just to make sure that it's true. So, and if you find a mistake, let me know. So let's look at just a few more simple, naturally occurring radioactive decay processes. So uranium-238 is the most abundant isotope of uranium, and it decays by alpha emission. So let's figure out what our other isotope would be. All right, so on the left-hand side, we have 238, and that has to equal to 4 plus something, the other mass numbers. So that's pretty easy. We can do that in our heads. That should be 234. So whatever this is, it's going to have a mass number of 234. And then the charge number, that's going to be 92. That's going to be 2 plus something, and that's also pretty easy to do in our heads. So that's going to be 90. So now we can go and take a look at the periodic table. This is the Web Elements website, which I like a lot. So we were at element 92, uranium, and now our new element has 90 protons, so that would be thorium. So we have identified our radiation product here, and we have thorium. Okay, so this is an example of alpha decay or alpha emission. Another example of a radioactive decay would be neptunium. Neptunium is, this isotope is neptunium-234, and it decays by electron capture. So our process then would look like this. So since electrons have zero mass, our mass number is not going to change. But since the electron has a -1, when we add those together, this is going to be 92. So this actually makes uranium because we already had uranium over here. So this is a different isotope of uranium. And one decay process that I didn't mention before, oh, this is electron capture. So one example that I didn't mention before is just gamma decay. So this one is a little less common. This just happens if you have an excited form of your element, like say dysprosium. It can be in an excited state in its nucleus and then relax, even though it doesn't change, and that's why I said this one is a little bit less noticeable, and it just releases the X-ray. So when you are balancing equations, the main things that we need to pay attention to are balancing the mass numbers and balancing the charge numbers. And everything else should fall into place.